Welcome to this class. Today, let us begin with equation of energy. We are looking at energy flux with a focus on thermal energy flux. Only the total energy is conserved. Therefore, for the conservation aspects, we need to look at total energy. From that, we need to extract out the thermal energy and write thermal energy in as a function of the parameters that we measure, that we have a handle on, and so on and so forth. That's the whole idea here. Okay, conservation itself is that of total energy, out of which we are extracting out thermal energy, because thermal energy happens to be of interest to us, and but energy conservation is the principle. Okay. Then we said, as we have already seen, there are two major approaches. One is shell balances, the other one is conservation equation approach. Here I did not show you the shell balances approach, as I showed you in detail for mass flux and momentum flux. Energy is anyway a scalar, so this will be somewhat closer to mass, but there are a lot more complications. Therefore, the equations would be a lot more complex. That's pretty much it. Okay. Then we looked, when we started out this chapter on energy flux, we looked at the three major mechanisms by which heat energy gets conducted. Heat energy gets transferred. One is by conduction, the other one is by convection, the third one is by radiation. Okay, let us move further. In the last class, I think we looked at the conduction equations alone. If conduction is the only method, if molecular molecular vibrations and motion is the only means by which heat is transferred, then the equations that we looked at or developed earlier, which is nothing but Fourier's law that we saw in all the three coordinate axes and so on, okay, that we could use. However, we need a lot more general, we need a formulation for a lot more general situation when there is flow and other things happening, and that's what we are going to do in this particular class. So, equation of energy, let's begin. Let me repeat a few of these things, it might be helpful. While discussing mass and momentum transfer, we saw that through shell balances, or although shell balances provided a physical feel for simple problems, the conservation equations were easier to employ for complex problems situations, especially in coordinate systems other than rectangular. That we have already seen. Now let us look at the equation of energy that can be applied in any heat transport situation. And we are going to begin the same way. We are going to consider the flow of a pure fluid, a pure fluid, it does not have anything else, through a stationary volume, which we know as the control volume, the same as the rectangular box or the cuboidal box in Cartesian coordinates that we first considered for mass and momentum transfer. The same control volume we are going to consider because it is intuitive. The rectangular Cartesian coordinate system is intuitive for us. So this is what it is. Again, x-axis here we have chosen the y-axis like this. Therefore, the z-axis by the right-handed screw rule, as you go from x to y, whichever direction a right-handed screw moves will be the direction of the z-axis, which is this. And then this is the cuboidal box that we are considering. X, y, z are the coordinates of this point. The dimensions of this box are delta x, delta y, and delta z. Therefore, the coordinates of this point are x plus delta x, y plus delta y, and z plus delta z. So this is the same control volume over which we are going to do our energy balances. So we are going to consider the relevant energies. If there are other energies, you need to add at this stage. Okay. So let us look at the usual energies that are involved. Internal energy, which can be visualized as arising from the vibrational, rotational, and potential energies of the molecules themselves. Okay, that's what we mean by internal energy. And recall from the course on thermodynamics, the abstract formulation for internal energy that happened to be initially an abstract formulation that happened to be very helpful for various different analyses, insights, design and operation of biological engineering systems. And then if you look at a statistical thermodynamics aspect, then you could relate the internal energy to the molecular motions. Okay. Then let us consider kinetic energy, which is associated with the observable motion or the bulk motion. So when a fluid moves, let us say, or a solid moves for that matter, there is a kinetic energy, you know, it is half mv squared or equivalent in fluid systems, and that is kinetic energy. That's the second energy that we are going to consider. Then we also know that right from school, maybe 6th standard, we know that there is something called a potential energy. Potential energy is energy by virtue of the position of the substance with respect to a certain datum level. To begin with, we are going to club it with the work done term for this particular derivation, because it can be interpreted as the work done against gravity. Okay, so we are not going to consider this separately here. We are going to consider it as work done against gravity. Energy that crosses the control volume boundaries as heat through conduction. Energy that is generated as heat in the control volume. Let us say it could be by metabolic activities or other aspects. Metabolic activities, because we are interested in biological systems. Metabolic activities are a significant source of energy generation within a system or a control volume. Work done against stresses. Okay, in fluid flow, there is stress, and work done against stresses and other aspects such as gravity is taken care of in the work done term. And other energies, say electrical, magnetic, surface energy, and so on and so forth, we are not going to consider them for now. Okay. However, if they are important for your system, you need to come back to the derivation at this point, add them here. Or if you can see where they get added, you could add them to the final equation. But to be confident, it's best to add them here and then do the whole set of manipulations again, the whole set of derivation again, to come up with the equation or the situation, let us say the representation that you would have significant confidence in. As I also mentioned, they can be added to the total energy term in the final equation by a mere algebraic addition. Here it would be straightforward, it's a scalar, so the other aspects may not cause too much of a confusion. If it's a vector such as momentum, it's not so easy to see unless you have significant insight into the way vectors behave. Okay, just by looking at a vector equation and trying to have a picture of what's happening is calls for certain orientation in those aspects or a lot of experience. Okay, so we'll not, but here it is only energy. You could even just add it. You need not come back and rederive the whole thing. Okay, so these are the energies that we will be considering. Internal energy, kinetic energy, potential energy. We are going to club it with work done. Energy that crosses this control volume boundaries as heat through conduction. Energy that's generated as heat in the control volume by metabolic activities, work done against stresses, and other energies. Now we are going to write the law of conservation of energy. Law of conservation of energy is energy can neither be created nor destroyed. So for a process, the energy, total energy before the process equals the total energy after the process. As simple as that. But we are going to write the left hand side in terms of the parameters of interest to us, the right hand side in terms of the parameters of interest to us. That's it. So the same way that we viewed mass as a certain quantity, momentum as a certain quantity, let's view energy as a certain quantity. Okay. So the rate of change of energy is the input rate of energy minus the output rate. So the net input rate plus the generation rate minus the consumption rate. Okay, so this is the net generation rate. So it's nothing but the same balance equation that is valid for any conserved quantity. Okay, any quantity in this case we have taken care of. What all can happen to it? Yeah, only if it is conserved can you write left hand side equals right hand side, and thereby this becomes valid. So we are going to consider the same equation for energy now. d dt of E is nothing but the energy that accumulates in the system or control volume. Okay, these things are important. Please make a note of these, and these will become a part of you only when you start doing applications, problems, and so on and so forth. We will do some of that as a part of the course itself here, and you'll have an opportunity to do that in the assignments. So note the in the system here, energy that accumulates in the system. This term, as I mentioned, is the energy, net energy that crosses the system boundaries, input minus output. And this is the energy generated or consumed in the system, or net energy generated in the system. And this, if you recall thermodynamics, recall the first law, okay, it said delta U equals Q minus W for a closed system. Okay. Why did we need to have Q and W? If you understood thermodynamics, you'd have understood that you needed two different formulations for heat and work, because they are not completely interconvertible because of the entropy and so on. Okay, so that is the nature of those. They are by nature two different aspects, and therefore we need to account for those two aspects separately. So they need to be separated as heat and work components, and we know from thermodynamics why we need to do that. Now let us separate the convection and conduction aspects. All these are to get it of the form or get it in terms of the parameters that are easy to measure or know. Okay, that's all. So we're going to write this as rate of accumulation of internal energy and kinetic energy. Okay, that is what we are going to consider. Those are the energies that we considered. If you go and look at the list, the rest we have coupled with others or whatever, equals the net rate of internal energy and kinetic energy in by convection. Okay, so we have separated out the convection from the conduction. We are going to take conduction with something else, plus the net rate of heat addition by conduction. Okay, net rate by conduction, here convection, here conduction, plus the net rate of heat addition by generation, say metabolic, minus the net work done by the system against stresses, gravity, and so on and so forth. Okay. Essentially, we have recast the right hand side in terms of the various separate components that go into determining these. That's it. Again, this is straightforward. We are looking at internal energy and kinetic energy, the accumulation of that in the system. And we have separated out the convection and conduction. This is the convection term, net rate of internal energy plus kinetic energy in by convection. And this is net rate of heat in or heat addition by conduction. And this is net rate of heat addition by generation. And this is the net work, negative of that, the net work done by the system against stresses, gravity, and so on. Okay, we have separated out the heat and the work components. Let's call this equation 4.2-1. Now we need to take the various aspects term by term, use input from thermodynamics and so on, because there is heat, there is work, a lot of interconversions and so on and so forth. We have an internal energy sitting there. And then after we do all this, we arrive at a useful expression for thermal energy transport. Okay. What I'm going to do is, okay, before that, know that the total energy is conserved, but thermal energy alone is not conserved. It helps to repeat this. Some of you might feel bored, you've already gotten it, but it helps to repeat this. We are looking at thermal energy alone where the total energy is conserved. The thermal energy transport is of interest to us in this chapter. That's the reason for looking at thermal energy. Let me say that I'm not going to present the lengthy derivation here. Okay. It is there in the textbook step by step. Okay. This derivation is certainly there. The shell balances are not there. Even in the book, because we had spent enough time on the mass and momentum aspects, shell balances for those, I did not spend time even in the book for energy transport. Here, I'm not even going to spend time for the conservation equation derivation. Okay, but it is given in the textbook step by step. So those who are interested can go and take a look at it. It is recommended, certainly. It is recommended that the learner goes through the derivation and convinces himself or herself that it is indeed the case. Here, we are in this course, we are just going to directly present the equation. It will turn out to be something like this. If we put everything together and go through about, I think it's about 7 or 8 pages of textbook pages of derivation with a lot of considerations, a lot of thermodynamics and so on and so forth. Okay. So we'll end up with the rate of energy gain per unit volume, which is given as dou T of rho, this is internal energy per unit mass, plus half V squared, equals the rate of energy in per unit rate of energy in the system per unit volume by convection, which is given as there will be a negative here, del dot rho V u hat plus half V squared. Okay, so this is the rate of energy in per unit volume by convection. This is the rate of energy in per unit volume by conduction. So that is del dot Q. That's quite straightforward. Okay, the same as conduction, and of course this appears as a negative term here by the way we have written this equation, plus rho times V dot G. This is nothing but the rate of work done on the fluid per unit volume, all are per unit volume, by gravitational forces, minus rate of work done on the fluid per unit volume by pressure forces, which is given as del dot PV, and also a negative appears here. This term accounts for rate of work done on the fluid per unit volume by viscous forces, and as expected the shear stress comes in here, del dot T dot V. Okay, tau dot V. Tau is a second order tensor, V is a first order tensor or a vector, plus Q dot other, say metabolic. Okay, this is subscript of Q dot, okay, the heat rate from other terms such as metabolic, minus the shaft work from other considerations, W dot, okay, shaft work rate from other considerations. Let us call this equation 4.2-3. Okay, this is what it will come down to after a lot of manipulation, 6 or 7 pages of manipulation, or maybe 3 or 4 pages for this, and then subsequent manipulation, another 3 or 4 pages. If you have any doubt in that derivation, please write to me or write in the forum, and then we can discuss. After that, you bring in some more thermodynamics and some more relationships and so on and so forth, the Maxwell's relations, equivalent and things like that. Then this equation can be written as, in a nice compact form, as rho Cv, substantial derivative of temperature with respect to time, equals minus del dot Q minus T dou P dou T at constant V hat del dot V minus tau double dot del V. Okay. Note, this is a dyadic product. Del is a vector, V is a vector. It's a dyadic product which will result in a second order tensor. This I'll talk to you about in a little bit. There's a double dot, a colon kind of a thing here. This represents a totally different kind of a manipulation between vectorial tensorial quantities. So I'll talk about this in a little bit. Plus Q dot other minus W dot other. This is equation 4.2-11. The double dot represents a scalar product between two tensors or equals. Okay, so that's a totally different operation here. It is represented in a short form as two dots. What does it mean? If you have tau tensor and del V dyadic product, you have these two quantities, and each one has 9 components, of course. Each one is a second order tensor. We know this, right? Now, if you take the scalar product between these two, then it is nothing but term by term multiplication. The other terms will drop out, and term by term the I alone will, I mean, the relevant terms alone will stay, the other terms will are not relevant, and these are the components of the double dot product, the scalar product between two tensors, tau xx dvx dx, tau xy dvx dy plus tau xz dvx dz plus tau yz dvx dy plus tau yy dvy dy plus tau yz dvy dz plus tau x zx dvz dou vz dou x, all these are doughs by the way, partials, plus tau zy dou vz dou y plus tau zz dou vz dou z. Okay. So these are, this is of course a scalar, therefore it's just a sum of all these quantities which will turn out to be a scalar. Let me show you how this equation appears. This is the form that has been expanded into its various components. This is a scalar, so you don't have components in each direction and so on and so forth. Energy is a scalar. But in three different coordinate systems, you have these equations directly presented in table 4.2-1. I'm going to show you that next. Please make a copy of table 4.2-1 and keep it at a readily accessible place for reference whenever it's needed. Okay, please do that, because we need to refer to this table often when analyses are being set up. And let me show you that set of tables, a set of equations in the table. So this is table 4.2-1, the equation of thermal energy. So this is for the rectangular Cartesian coordinate system. You have it of this form, the same equation written down as individual components, okay, because we can directly substitute the individual components. That's the whole point here. So these are the various terms. This is we call this A1, and when in the same way in the earlier case, we have an equation for the simpler situation. This is in terms of shear stresses, which are not directly obtainable, or you would like to have these in terms of velocities. That you could do easily if the fluid happens to be Newtonian, and when rho and k are constant, density and thermal conductivity are constants, then you could write it off this form, following pretty much similar arguments that we did for the momentum flux or the momentum balance equations of motion. So this is for the rectangular Cartesian coordinate system case. You could always convert it into cylindrical coordinates by using the principles given in the appendix or using the methodology given in the appendix. These are the equations B1, B2. The first one is for a general situation. The second one is for a Newtonian fluid when rho and k are constant. Then for spherical coordinate systems. Please make a copy of this set of tables and keep it as a part of your notes. I think we'll stop here for this class. Been at it for some time. We'll take things forward when we meet again. See you then.